mouth was. This is going to be a fairly short talk, mostly because I thought I haven't actually given a talk for a while, and I'm always sort of bullying people and saying you should give talks, and I thought it was time to actually put my sort of time where my mouth was. And I actually also remarkably had something to talk about. So yeah, I've got hold of this board that has this SB0256 speech chip on it. So that's given me a dose of retro speech, taking me back to my Spectrum days in the 1980s. So I thought I might share some of that with you. So yeah, so today we'll take a look at the hardware, both sort of then and now. Take a look about how this stuff actually works, and then how we can be a bit more lazy about it, and then actually demo it so you can see, well, you hear this stuff working. And for bonus points at the end, I'll compare it with sort of state-of-the-art text-to-speech, so you can just see how much we've progressed since the 1980s. So then, let's start with the hardware. So back in the 1980s, if you had a C64 or a Spectrum, you might have seen this beastie here. It's a Current MicroSpeech, and it allowed you to make your computer speak. It was supported by a few games, and it had a fairly rudimentary speech engine. It sounded very robotic. And it worked by using allophones. So allophones are sort of parts of speech, and you would assemble them together and make words. And as you see, that could be fairly tedious, but it was supported by a few games. So you could have speech in some games that they supported it, and some games like Booty actually had a completely different game if you had the MicroSpeech attached. So how did it work? So it had a ULA, so it wasn't just the raw SP0256 chip. And it assigned, it basically grabbed the sort of top area of the Spectrum RAM, and in BASIC at least, you could assign this reserved variable to make it speak. And you could give it text that looked, sort of strings that looked like text, and then if you wanted more control of pronunciation, to say a particular allophone, you could put this expression in brackets to say that you know, this here is this, so this DTH brackets means the part of this. And it gave you basically 63 different sounds, 5 of which were pauses of various length. You could use uppercase and lowercase to give you a slight pitch modulation.
Excuse me, Dave.
Yeah.
Would you like questions at the end, or can I also ask questions during the talk? What do you?
No, go ahead.
Because you went over ULA, and I know UCLA and other things of ULA, but I have no idea what you mean with ULA.
All right, sorry, yeah, yeah, it's basically
Unified logic array.
Yeah.
So I'm glad I wasn't the only one that didn't know.
I just asked.
Sorry, I worked at Ferranti, which made ULAs.
Yeah. So you can think of it as a very early FPGA, but you can only program it once, if you like. And I know that you can maybe give a slightly better explanation at the end, if you like, John. So yeah, basically a bit of programmable logic, a single chip that had a bunch of functionality in. And yeah, and so I should explain my acronyms. So thanks for the question. Okay. So here, what do you, if you were going to use it, what might it look like? So if you can say, okay, wise guy, this is it, and this is an example I've stolen shamelessly from Wikipedia, you'd have sort of text like this. So, okay, this is wise guy, this is it. And then you'd assign it to this $S variable, and it will go ahead and speak it. So you could sort of read it just about, but it's a bit painful. You had to work out exactly what the right allophones were. You couldn't just feed it raw text. So moving to the present day, there's this beastie called the MG05. It's a card that's produced by Steve Gieler, I think, who works by the name Mr. Jelly on Tindy. And he's produced this card here, which is the one I've got on my RC2014 today. It's got one of these SP0256 LA2 chips, which are sort of retro now. Most of them you'll find are sort of new old or been reclaimed from old hardware. There's a bunch of fakes about. But this is the chip that actually does all the work. What's nice about this card is it has a built-in speaker, so you can just plug it into your RC2014 and go. It has a clamp to drive that and a bit of address decoding logic. Now this isn't quite as friendly to use as the old Spectrum card, because it's basically a bare SP20256 directly on the RC2014 bus. So you're writing direct to this chip. So you write a byte to the output port to speak an allophone, and then you have to check these two imports to see when it's ready to get the next one. So there's one which is standby when it's finished speaking, or when also when this LRQ signal goes to 0 and the buffer's empty. So how do you say hello world? So using the way the description of the allophones on the data sheet, it would look something like this. So each one of these letter groups is an allophone, and you have to go and work out, okay, well, the H in hello is that's HH1, then the L that's AX, then they've got double L, that's hello, then O allophone is this. So there's a lookup table that's provided on the data sheet. It's a bit tedious. It's the sort of thing I did back in the day with the Curragh MicroSpeech, but I guess I was more motivated then. I'm feeling lazy now. And we'll get on to a bit later how you can be lazy. So using it from BASIC, again, it's a bit less friendly than the MicroSpeech. Basically, what this example does is it has a bunch of allophones coded as decimal. It reads them out from data, stuffs them into an array, and then it reads for that array. It checks this line 80 here. It's checking, is the standby high? Can I actually write to the output? And if it's ready, it just busy waits there. If it's ready, it goes and sends the next allophone to the device, and it repeats. And it does that for every character in the array. So it's fairly simple, but the tedious bit is working out what these numbers here are. So how does this chip actually work? Yeah, I've mentioned allophones before, and you may not have heard that term. You may have heard of phonemes. And I must admit, back when I first did this stuff, I didn't know what the difference was. But apparently a phoneme is technically a unit of sound that distinguishes one word from another in a particular language. So what's a phoneme in English may not actually be a phoneme in, say, French. And an allophone is the actual sound that makes up a possible phoneme. So the allophone is the more, if you like, concrete thing. And that's why the data sheets of these things talk in terms of allophones, I guess. Although I don't think they actually supported more than English. Though I've never tried to do any sort of French or anything with the the chip. It's too long saying SP0256 every time, but it may or may not be possible. So it's designed to model the human vocal tract. So it's not actually playing samples. There's this technique called linear predictive coding that's used to model the voice. And what it's actually done is these allophones are encoded based on encoded real speech of the allophones, and it then used a filter to play this back. It's got a 10 kilohertz sample rate, and it uses a 12-pole filter. And I stole this again from Wikipedia. I don't know the total ins and outs. I guess the interesting about linear predictive coding is it came on to be the basis of voice over IP. So it's a way, if you believe Wikipedia, it's still one of the best ways to actually represent speech at a low bit rate. It dates back to the 1940s, and it has a fairly bizarre, well, to me it sounded bizarre, assumption that a speech signal is basically a buzzer at the end of a tube with occasional hissing and popping sounds. And that apparently it sounds like a fairly simple model, actually works really well. And then you break up these it's a frames about 30 to 50 times a second, and that gives you a model that you can play a speech, and you'll see how good at the end, how good it or not it actually sounds. But yeah, this is still used for voice over IP today, although I guess the sample rate will be somewhat higher than supported by the chip we're using, or I'm using. Yeah, so you saw that Hello World example. that was about 10 allophones for 2 words. You could if you had a chunk of text, you can imagine that'd be fairly tedious to try and translate that. So I guess the obvious question to ask is, well, I'd rather not do that. Can something do it for me? And there are 2 ways. You can actually do it in hardware. There was another chip called the CSS256AL2, and that actually implemented this text-to-speech algorithm. So it was a companion chip, I guess, to the SPO chip, and you would use them together, and you would feed ASCII text into this chip, and it would spit out allophones and then feed them to the SPO chip. Now, I've not done anything with this, but Scott Baker has, as he seems to have done almost everything with the retro computing, he's got a board that he's built that does this, and it's basically a microcontroller that uses some fairly simple, I think, algorithm as sort of heuristics to work out, okay, for this sound, it's probably this allophone. And that seems to give reasonable results. I don't have one of these chips. They seem to be kind of hard to get. So I've not tried to replicate that. So, the next way you could do it is a thing called pronouncing dictionaries. So that's a dictionary that gives you the pronunciation for every word. And so, you could take a string like hello world, you break it up into words, you look up each word in the pronouncing dictionary, and so so hello gives you that, world gives you that. You add some pauses between the words, and then you in this case, because you're probably like me, a bit unlucky, your pronouncing dictionary you have its own pronunciation symbols, so you work out, okay, how do they map to the set I've got for the SPO chip, and then you just convert that to the decimal representation. And there was actually a project that already did that. This one here, I've got the link, and that was designed to work with an Arduino board, apparently, that also supports this chip. So that seemed like a good route, but there are a couple of issues with it. One, if you want to say things like RC 2014, which I did for surprising reasons, because you find that obviously the word 2000 is in the dictionary, but 2014 isn't in the dictionary. So just putting raw text into this algorithm didn't work, and also acronyms are generally not in the dictionary. So I forked the repo and I did a bit more work to convert numbers to words. So it actually, it would take 2014 and actually write out words 2014, and then convert acronyms to letters. So there's my fork there, if you want to look at it. It's still pretty ugly. There's a lot of stuff you can do to make it better. Right, but demo time. So I thought it'd be, I don't know, amusing or not, to use part of the abstract. It's quite slow, so I just took the first 2 sentences from the abstract, and I'm showing you the text now because you may not. It's not the most intelligible output, so you may need. It's good to know what it's saying in order to understand it. Now, hopefully, it will actually play the sound. If you don't hear anything on the next slide, just please let me know.
In the early 1980s, Yamazi Ekman and the Eti Hamukopi to you and to an expansion owned by a UK company. Nowadays, text-to-speech is the main and easily available, but to me at least back in the 1980s, having your computer talk to you was like something out of Star Trek.
Back in the early 1980s, your ZX Spectrum and C64 could speak to you thanks to an expansion sold by UK company Curra. Some games even took advantage of this. Nowadays text-to-speech is mundane and easily available, but, to me at least, back in the 1980s having your computer talk to you was like something out of Star Trek.